Hi, in this video we'll go over the solutions for this week's discussion handout on perceptrons. There's only one question in this handout, so let's jump right into it. In this question, we're classifying whether movies will be able to profit or not. So given a movie, we're either going to say that it will profit, that's this yes label, or it won't profit, which is this no label here. As for the features, we have two critics. Unsurprisingly, they're called A and B, and they give a score between 1 and 5 inclusive. So this means that the critic's score will help us determine whether or not the movies will profit or not. Alright, so here's our training data, and inside the training data we have 5 movies. They're shown here. In the first part, we're simply asked to plot the data along the feature axes. In this case, our feature space is 2D since we only have two different features here. And so let's say that the horizontal axis, that's this one here, that's the score for critic A, and the vertical axis here, that's the score for critic B. Let's plot the points shown in this table here. We'll start with the positive labels where the profit is equal to yes, and we'll represent these labels with a blue plus sign. So let's start with ghosts. For ghosts is at the point 3, 2. 3's here, 2's around here, so let's put a plus sign here. For not a pizza, that's at the coordinates 3, 4, so 3, 4, that's about here. And endless maze 2, 3, that's around here. Okay, so now we got the positive labels. Now we have to plot the negative labels where profit equals no. I'm going to switch the color to red. And let's plot the no labels as red minus signs. So that would be pellet power and pack is back. For pellet power, that's at 1, 1, which is down here. And for pack is back, that's at 4, 5, and that's up here. Okay, so here's our training data represented in a 2D plane. Is this data linearly separable? Meaning, is there any way we can draw a line to separate the blue plus signs from the red minus signs? Well, you can try drawing lines here, but the answer is no. So no, the data is not linearly separable. Okay, so now we're going to use a perceptron to classify our data. We're going to use the multi-class formulation here, even though we have two classes, which explains why we have two different weight vectors that are opposites of each other here. The features we are going to be using for this problem are the score from critic A, the score from critic B, and in addition we're going to add one more feature that's going to be called a bias feature. What the bias feature is for any input, it just takes on the value 1. So this here, this is going to be the feature vector f of x. The importance of this bias feature here is that we are not restricted to a hyperplane that only passes through the origin, but instead we're able to shift it up and down according to the bias weight, which is this term here. So the weights here consist of 3 terms. They match the 3 terms in the feature vector shown here. And so to make it clear that we're adding this bias feature, let's go to our training data here and add a 1 in front of all the scores we get for our critics for each of the movies. And this is just to remind ourselves that we actually need 3 components for every input. For this problem, we need to identify first what is the first training instance in which we update our weights, and then next we need to actually update the weights for the first update. Remember that a weight update only occurs when we mispredict an input. So let's start with the first movie here, pellet power. To make a prediction, the perceptron computes the dot product of the feature vector here with each of the weight vectors here. So let's first consider the yes case. For the yes case, we take the dot product of f of x, that's 1, 1, 1, and the weight vector for yes, which is currently this one here, -1, 0, 0. So when we take the dot product of this, we end up with -1. Likewise, for the no case, the feature vector is also 1, 1, 1, and the weight vector, well, this time we need the weight vector for no. The weight vector for no is just 1, 0, 0. And when we take the dot product between these two vectors, we get positive 1. The label we're going to predict is the one that produced the higher dot product because the dot product measures similarity between the vectors, and so we end up predicting no. And our true label here is also no, so our classifier predicted correctly based on these weights. When we predict correctly, we make no changes to the weights. So we're done with our first data point, and we move on to the second data point, which is the movie Ghosts. For this movie, we're going to do the same thing as the previous part, and we're going to take this feature vector and compute the dot product between this feature vector and the two weight vectors here. For the yes case, we're computing f of x dotted with the weight vector for yes. And so here we have 1, 3, 2 dotted with -1, 0, 0. This produces a value of -1. For the no case, we need to compute the dot product of f of x and the weight vector for no. So the feature vector is 1, 3, 2, and the weight vector for no, that's 1, 0, 0. And so the dot product between these two vectors, that's equal to +1. And so here, the classifier will also predict no, because +1 is greater than -1, but the actual label here is yes. So our classifier made a mistake, and so we need to make a change to both weight vectors here to account for the fact that we made that mistake. For the misclassified predicted label, that's no here, we want to shift the weight vector of no away from the feature vector, and so all we do is subtract f of x from our weight vector here, and this gets set to our new weight vector, w no. So here w no is 1, 0, 0. We're subtracting 1, 3, 2 from this vector, and we end up with 0, -3, -2. So this will be the new weight for no after the update. Similarly, for the actual label yes, we want to push the weight vector of the actual label towards the feature vector, so we add the feature vector here. So here we have -1, 0, 0. We add the feature vector 1, 3, 2, and we end up with 0, 3, 2. And that's the new weight for yes. Note that it is no coincidence that these weight vectors are always opposites of each other. That's why in the binary case, we can simplify the binary perceptron to only store one copy of these weight vectors, because having one of these weight vectors allows us to determine what the other weight vector is, since they're just opposites of each other. And I just noticed I'm being a little lazy with notation here, so let me go back and mark which components are actually vectors in these calculations. Most importantly, the dot product happens between a feature vector and a weight vector, and these updates here, they're also updates based on vectors. So let me mark all of them with arrows. So now hopefully the operations are a bit more clear. So to wrap up this problem, the first training instance at which we updated our weights, that would be for the movie Ghosts. And the updated weights, we put that in our table up here. Before we go into the next part, we're going to transition from talking about the two-label multi-class perceptron to the actual binary representation of the perceptron, which means the following. In the multi-class case, we took the dot product for both weight vectors, and we chose the label with the highest value. Let's consider this case here. Where is the breakoff point located where we are right on the boundary of choosing yes or no? That would be when this dot product between the feature vector and the weight vector, if the dot product is 0. If the dot product goes slightly positive, then we would predict yes. But on the other hand, if the dot product goes slightly negative, then we'll predict no. And so in the binary case, we only need to keep track of one of these weight vectors. Let's say it's the weight vector for yes. In this case, if the dot product between the feature vector and the weight vector, here the weight vector again is for yes. If this dot product is greater than or equal to 0, then we predict the positive class, which is yes. And then likewise, if the dot product between the feature vector and the weight vector, if that's less than 0, again, the weight vector here is the weight vector for yes, then we're going to predict no. Okay, so here we have the condition for how we predict in the binary representation. We're going to use this in the following problems. The next part asks us to determine which scenarios the perceptron can handle with the given feature representation. As you recall, the feature representation f of x, that has three components. The first component is the bias feature, which is always 1 for any input. The second feature is the score for critic A, and the third feature is the score for critic B. And just as a reminder, for the binary perceptron, to predict a positive class, that is, let's say yes, we need the condition that the weight vector times the feature vector, this has to be greater than or equal to 0. So based on this condition here, it's not hard to see that the perceptron learns a linear decision boundary. So if we are able to find a hyperplane that separates out the data in these situations here, then we are good to go. In this case, the data is two-dimensional, so we can visualize the data on a 2D graph and see if we can fit a line through it. Note that the addition of this bias term does not raise the dimension of the feature space by 1. You can just think of this bias term as a intercept to the hyperplane, so that allows us to shift the hyperplane up and down. So let's consider the first scenario here. Our movie will definitely be a success if the total of the reviewers' scores is greater than 8. Well, when can that happen? That can only happen when, say, both of the reviewers give a score of 5, or if one of them gives a score of 4 and the other gives a score of 5. So we have these three cases here. In all the other cases, the total of the scores is going to be 8 or less. So if we plot this out in a two-dimensional grid, let's say this is the score for critic A and this is the score for critic B. These 3 points are going to lie somewhere up here, and all the other points are going to lie to the left and below that. So let's put that here. So is there a line that can separate the blue plus points from the red minus points? Well, sure there is. There's this line here. And so yes, the perceptron can classify perfectly in this scenario. Now let's see if we can find a set of weights for this line here. Recall the binary decision rule for a positive class. That is, the dot product for the weight vector times the feature vector has to be greater than or equal to 0. Here, each of these vectors has 3 terms, and so we can expand this out explicitly. By doing so, we have that the weight for critic A times the score for critic A plus the weight for critic B times the score of critic B plus the weight of the bias times the feature value of the bias, that's always 1, so we don't need to include that. That's greater than or equal to 0. Based on this problem, we predict a positive class, that is, if the movie will succeed, if the sum of the feature scores is greater than 8. Notice that this condition and this condition look pretty similar. If we can just figure out what a set of values are for the weight terms, we're done. So here we should set the weight for critic A to be 1, the weight for critic B to be 1. That way we'll get this here. What should we set the weight of the bias to be? Well, in this condition we need it to be strictly greater than 8, but here we have a greater than or equal. That means we need to allow some leeway here. And so if we set the weight of the bias to say minus 8.5, then we basically have the condition here, f of A plus f of B is greater than or equal to 8.5. That basically captures the same effect here, because all the feature values are going to be integers. And so this condition will hold when this condition holds too. And so this set of weights is an appropriate choice for this line here. So let's write that down as an explicit weight vector. If you have this weight vector for this line will be able to separate the data. Okay, so let's circle this as a correct choice. Let's move on to the second subpart, which says that the movie will succeed if and only if each reviewer gives either a score of 2 or 3. Well, the points where the movie will succeed are if the movie is on the coordinates 2, 2, 2, 3, 3, 2, and 3, 3, because in these four coordinates, both reviewers gave it a score of 2 or 3, and for any other coordinate, well, at least one reviewer didn't give it a score of 2 or 3. So we can plot this out as well. Here's our axes. Let's say that these 4 points lie about right here, and all the other points fall around it. Can we fit a line that passes through this data? No, we can't. So the perceptron cannot classify this scenario correctly with the current feature space, and so let's cross this off. Let's move on to the third subpart, which says that the movie will succeed if and only if both reviewers agree. So the points where the movie will succeed are either 1, 1, 2, 2, 3, 3, 4, 4, or 5, 5, because in these 5 scenarios, both the scores of the reviewers agree. So if we plot this out, these 5 points lie on the diagonal here, and all the other points lie around it. Can a single line separate this data here? No, it can't. So again, the perceptron cannot classify this scenario correctly with the current feature space, and we'll cross this out. The final part asks us to consider the same 3 scenarios that we saw before, except we're using a different feature space shown here. Here we still have a bias term, but for each critic's score, instead of having a single digit from 1 to 5, we'll replace it with 5 different indicator features. So for A, there's 2 of them that are shown here, but we still have the one f of 3a, f of 4a, and f of 5a. The indicator features return 1 if the feature is on, and otherwise it returns 0. So let's write out this feature vector explicitly here. So here's our feature vector. It has 11 entries here, and one thing to note is that only 3 of these components are ever going to be on. There's going to be the bias feature, one single component for A, that is one of these 5 values here, and one of the 5 values of B will be on at one single time. So for example, if we had critic A that gave a score of 3 and critic B that gave a score of 3, how would the feature vector look like? Well, it should look something like this. Alright, so the features that are on are the bias feature, the indicator feature that the score given by A was 3, and the indicator feature that the score given by B was 3. So keep that in mind. All of these features will only ever have 3 terms on at the same time. Okay, so our feature vector has 11 entries, and we're working in 10-dimensional space. So we can just visualize this problem in 10D space, look for a hyperplane that separates the data, and we're good to go, right? Well, that's definitely one way to do it, but most of us can't visualize 10D space, so we're going to need another plan. And this plan will involve trying to think about weight vectors that we can use. The first scenario to consider is that the movie will succeed if the sum of the reviewer's scores is greater than 8. So, where can we start with finding a weight vector? Well, one important thing to note is that before, the features carried on the actual weight of the score. So we had a notion that a 5 had more value than a 1, but now our features are either 0 or 1. We lost the notion of the weight of a score. Well, if it's not present in the feature vector, where else could it be? It has to be incorporated in the weight vector, right? So this gives us a reasonable start here. For all the non-biased features, let's set the weight equal to the corresponding score that the critic gives. So here we have 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. And what should the bias term be? It turns out we get to the same conclusion as before, and the bias term should be minus 8.5. Does this work? What if critic A gave a score of 4 and critic B gave a score of 5? Well, if this happens, the features that are on are the bias feature, the feature for the score of A being 4, and the feature for the score of B being 5. Here the check marks indicate that the feature is on, meaning it has a value of 1, and the absence of a check mark means that the feature value is 0. So when we take the dot product, we only have to consider the terms marked with the check mark, and the dot product will just be 1 times 5, that's 5, plus 1 times 4, that's 4, with a total of 9, plus 1 times negative 8.5. Well, that gives us a total of 0.5, meaning it's positive, and we classify it as a success. So that's exactly what we want. And you can work out the other examples, but yes, this is indeed an example of a weight vector that classifies this scenario correctly. How about the next scenario, where the movie will succeed if both the reviewers give either a 2 or 3? Here, the notion of a weight of a score is not particularly important, but since we have indicator features, one natural thing to try instantly would be to associate a positive weight to the features related to a score of 2 or 3. Meaning, for these 4 terms, let's assign this equal to a positive value. Let's, for simplicity, set it equal to 1. And let's also make all of the non-2 or 3 scoring weights equal to 0. So now we just need to think of an appropriate bias value to put here. Well, let's step back and kind of think of the conditions that we have. Here we mainly have 3 conditions to consider. Let me write them down here. The first condition is that neither reviewer gave a score of 2 or 3. The second condition is that only one reviewer gave a score of 2 or 3. And the third condition is that both reviewers gave a score of 2 or 3. Here I want to write out the dot product explicitly. And note that we don't have the bias value, so I need to leave it in terms of this W bias term. Well, if neither reviewer gave a score of 2 or 3, that means that the weight for both the score features for both critics would be one of these 0 terms here, right? And so that part in the dot product would be 0, and all we'll have left is just the bias term. So this would be W bias. When one reviewer gives a score of 2 or 3, that means one of the features here is on, and then one of the features in here is on. Which means that the dot product, remember that the feature values are all 1. For the feature that's on here, that contributes a score of 1 for the dot product, and the bias also plays a role. So here we have 1 plus the bias weight. And now if both reviewers gave a score of 2 or 3, then we have 2 features on in this range, and so when we take the dot product here, we have 2 plus the weight of the bias. So what we need to do is we need to find a value for W bias that separates out the last condition, which represents all the profitable movies, from the first 2 conditions, which represents the non-profitable movies. And so what value of W bias would set this to be a positive value, but this to be a minus value? Well, let's try W bias equal to minus 1.5. If we set these terms to minus 1.5, then these 2 would be negative, and this one would be positive, which is exactly what we want. So let's put a weight of minus 1.5 for the bias term. This is one weight vector that correctly satisfies the condition that we have. So it turns out that using this feature space, the perceptron can learn this situation correctly. Lastly, we have this situation where the movie succeeds if both critics return the same score. It turns out that the classifier cannot classify this situation, and we can actually prove it by showing the relationship between 4 points. Consider the following 4 points. We want the point where critic A gives a score of 1, critic B gives a score of 1. The second point would be the critic A gives a score of 2 and critic B gives a score of 2. Critic A gives a score of 1 and critic B gives a score of 2. And critic A gives a score of 2 and critic B gives a score of 1. So if the movie succeeds, if the reviewers give the same score, then this movie succeeds, this one also succeeds, and the last two don't succeed. So we can write the decision rule for each of these 4 data points. Let's take the first point. In this case, since this is a positive example, we want the dot product greater than or equal to 0. And the dot product here, remember there's only 3 terms because only 3 of the feature values in the feature vector are ever on at the same time. And so the terms that are on here are the bias term, has the weight of the bias, times the feature of the bias. Well, the feature of the bias is always 1, so we can ignore that. Then we have the weight subscript 1a times the feature subscript 1a. Well, the feature is an indicator feature, so we don't need to include that. Similarly, we have the weight subscript 1b. And this has to be greater than or equal to 0. Likewise, for this point, we have that the bias weight plus the weight subscript 2a plus the weight subscript 2b, that has to be greater than or equal to 0 as well. Over here, this is a negative example, so we want the dot product less than 0. And similarly, we have the bias weight plus the weight subscript 1a plus the weight subscript 2b. And for this point, we have the weight of the bias term plus the weight subscript 2a plus the weight subscript 1b. And again, that's less than 0. Okay, so now we have these 4 decision rules. What happens when you add these 2 together and these 2 together? Well, notice that on the left-hand side, the sum here and the sum here, they're equivalent. They have the same terms. However, this condition guarantees that the sum is greater than or equal to 0 here, but here it's less than 0. So here we have a contradiction. And so we can't even find a setting for this subset of weights that can classify the situation correctly. That means we won't be able to find a setting for all of the weights that will classify this correctly. And so it turns out that there is no such weight vector that can get this data separated. And so let's go back to here and let's mark these 2 as correct and this one as wrong. All right, that's it